Unpacking unexpected discoveries, reshaping our understanding of everything from semiconductors to distant planets. Arjun, our first paper really challenges a fundamental assumption in thermal physics.
Arjun, this research titled When Heat Goes Astray, Non-Local Heating in a Semiconductor, dives into how heat behaves at tiny scales, which is critical for future electronics.
That's the common assumption they challenge. We've presumed the heat source and hotspot perfectly coincide, especially when components are larger than phonon-anine-free paths.
So, a tiny heater means a hotspot exactly there? No questions asked?
This paper shows that isn't always true at micrometers.
Wait, so this paradigm of heat locality breaks down? That's a big deal for designing microprocessors, where every nanometer and every degree counts.
It absolutely is. If heat doesn't stay put, our thermal management for advanced devices might be flawed. It forces a fundamental rethink. The researchers found that non-local heating occurs in contradiction to Fourier's law. Heat can travel further than expected, not just diffusing, but sometimes ballistically, like particles flying across the material.
Ballistic phonon transport? Heat effectively teleports? That's quite a leap from intuition. And they state something surprising here. Remarkably, the non-local heating can exceed the laser-induced local heating. A distant heat spot can be hotter than the source?
It's profound, suggesting heat transfer mechanisms are far more complex than understood, even far above cryogenic temperatures.
This ballistic phonon transport means stacked 3D chips might funnel heat unexpectedly, creating distant hotspots. For chip designers, simulating heat flow needs a completely new model.
So, building compact electronics isn't just shrinking components, it's fundamentally rethinking heat management when it breaks the rules.
From fundamental heat physics, let's switch dramatically to something else, the ethics of AI. Arjun, what's next?
We are moving to a paper tackling honesty in large language models after unlearning, a crucial process for data removal and safety. It questions if we can trust what they forget.
Okay, unlearners can lie. That title grabs attention. It sounds like something from sci-fi about rogue AIs. What exactly are we talking about?
Maya, this paper addresses a critical challenge in AI, ensuring that when we remove specific, often harmful data from an LLM, it genuinely unlearns while remaining honest.
The goal of unlearning in large language models is to remove specific training data, like sensitive information, without degrading overall utility. It's selective memory erasure for safety.
So the model forgets something bad but stays useful? A delicate balance. But the paper finds existing methods often hallucinate, generate abnormal token sequences, or behave inconsistently. That's not just forgetting, it's erratic behavior, potentially worse than retaining data.
This is a serious problem. These behaviors, as the authors note, are often associated with dishonesty. The model gets confused or fabricates, eroding trust.
They propose a formal definition of unlearning honesty, preserving utility and honesty on retained knowledge, and ensuring effective forgetting while acknowledging limitations and responding consistently about forgotten knowledge.
So not just deleting, the model needs to say, I don't know, instead of making things up about what it forgot.
I see a phrase that summarizes it, preserving both utility and honesty on retained knowledge. That's the baseline. Extending honesty to remove data is the challenge.
That's right, and their evaluation across 9 methods shows all current methods fail to meet these standards, highlighting a significant gap in LLM safety.
To fix this, they introduce REVA, a representation alignment procedure. REVA fine-tunes unlearned models to better acknowledge forgotten knowledge.
significantly increasing rejection rates for those topics. For developers, this means retraining the model on how to behave after forgetting, teaching it humility about its gaps.
From abstract LLM honesty, let's dive into something visually dynamic and precise, reconstructing table tennis in 4D. Arjun, this sounds like a hacker's dream for sports analytics.
It's fascinating, Maya. This next paper details a pipeline that recreates entire table tennis matches with incredible spatial and temporal detail from standard video.
This paper, TT4D, a pipeline and dataset for table tennis 4D reconstruction from monocular videos, sounds specialized. What makes capturing table tennis in 4D so challenging?
Table tennis has fast, small movements and an easily obscured ball. The authors present TT4D, a large-scale, high-fidelity table tennis dataset from over 140 hours of broadcast video.
This dataset isn't just video. It provides multimodal annotations like high-quality camera calibrations, precise 3D ball positions, ball spin, time segmentation, and 3D human meshes over time. Unprecedented detail for the sport.
Wow! Reconstructing every aspect of physics and movement. A goldmine for understanding player mechanics.
It also says this data provides a new foundation for virtual replay, in-depth player analysis, and robot learning. I'm surprised by robot learning, teaching a robot to play or something else.
That's right. Understanding human dexterity at this micro level offers crucial insights for teaching robots complex manipulation, moving beyond pre-programmed motions. The key is their novel reconstruction pipeline. Previous methods struggled with occlusions by segmenting 2D tracks first. This paper lifts the entire unsegmented 2D ball track to 3D immediately.
So, instead of screen position, then depth, they directly understand the 3D path, even if parts are hidden?
And they state, this lift-first design is necessary, as our pipeline is the only method capable of reconstructing table tennis gameplay from general view broadcast monocular videos. That's a strong claim.
It underscores the problem's difficulty. Inferring 3D trajectories and spin from one camera with fast occluded objects needs sophisticated learned networks that predict physics. One application is estimating the racket's pose and velocity at impact. Coaches could use this for precise analysis of swing angle and power, providing data-driven feedback impossible manually.
Or training AI agents in simulation to predict returns based on subtle wrist movement. This precision opens avenues for human training and AI development in dynamic environments.
That's incredible detail for a tiny ball on a table. Now let's scale up dramatically, from ping pong to planets. Arjun, tell us about Neptune's gravitational dance and solar system history.
A huge shift, Maya, but equally about understanding motion and its profound implications. This next paper explores how Neptune's early migration shaped countless celestial orbits.
All right, Arjun, jumping from AI to astrophysics with numerical estimation of the capturability of Neptunian mean motion resonances, unraveling our cosmic backyard's ancient history.
This research uses numerical simulations to understand how Neptune's early outward migration, billions of years ago, gravitationally captured distant objects into stable orbits. These resonant populations of trans-Neptunian objects are dynamical archives. Their orbits hold clues like cosmic fossils about the early migratory history of the solar system.
So, by studying icy bodies beyond Neptune, we deduce where Neptune used to be and how it moved? Incredible detective work. The paper mentions a certain threshold for capture, increasing with faster migration. Is it a cosmic sweet spot where objects get pulled into a stable dance with Neptune?
That's right.
It's a delicate interplay of orbital mechanics. Too fast or far, and the gravitational resonance might not be strong enough to capture an object into a stable, repeating pattern relative to Neptune's orbit.
They found that capture efficiency shows little dependence on the migration rate once eccentricity is suitable. It depends on the p-value, linked to orbital period ratio and heliocentric distance.
Counterintuitive. So it's more about the object's initial orbit and position, not how fast Neptune moves?
And these summarize this complex dynamic into something usable. Here, we derive for the first time a simple empirical expression to calculate its centricity threshold and the capture efficiency.
A significant achievement. This formula provides a quantitative framework for understanding these gravitational interactions, moving from complex simulations to a generalizable tool for astrophysicists. This framework is crucial for solar system formation. Combining it with observations, planetary scientists can refine theories of planet formation and reconstruction of the primordial planetesimal disk.
Like linguists reconstructing ancient languages from fragments. Here, orbital mechanics reconstructs cosmic history, piece by gravitational piece. Math and deep time connected.
From planetary migration back to Earth and another AI challenge, computers identifying objects in an open world. Arjun, what's next?
VLSAM-3, a fascinating step towards generalist vision systems. It enables AI to recognize objects it's never explicitly seen before, vital for real-world applications.
Our final paper, VLSAM v3, Memory-Guided Visual Priors for Open-World Object Detection, tackles a holy grail of computer vision, making AI see the world like humans, identifying anything.
Our final paper, VLSAM v3, Memory-Guided Visual Priors for Open-World Object Detection, tackles a holy grail of computer vision, making AI see the world like humans, identifying anything. The paper distinguishes open vocabulary detection with a test time category list from open-ended detection, requiring generating categories during inference, both crucial for truly generalist AI.
So, open vocabulary is find a platypus, knowing it's an option. Open-ended is what's this weird animal? Am I right?
It highlights a problem. Existing methods rely primarily on coarse textual semantics and parametric knowledge, which often provide insufficient visual evidence. Descriptions aren't enough when appearance varies.
Exactly. A fluffy dog doesn't capture infinite variations. Visual priors are essential, especially for fine-grained appearance variation, rare categories, and cluttered scenes.
VLSAM v3 augments detection with retrieval-grounded external visual memory. It pulls up relevant visual prototypes, creating sparse priors for instance-level spatial anchoring and dense priors for class-aware local context.
So the AI has a visual Rolodex it consults rather than just matching text, like humans generalizing by comparing new things to past visual experiences.
I like this phrasing, memory-guided prompt refinement, enabling a shared retrieval and refinement mechanism. Not just retrieving, but refining understanding of the new visual prompt.
This is a powerful approach. This dual mechanism allows the system to flexibly adapt to new objects and contexts, bridging the gap between what it knows and what it needs to learn on the fly. The system shows particularly strong gains on rare categories. For builders, this means deploying detection models in niche applications, identifying uncommon defects without massive custom datasets.
So instead of thousands of images per item, a model extrapolates from a few examples or descriptions by leveraging visual memory, a huge efficiency leap.
From heat and semiconductors to LLM honesty, 4D table tennis, planetary dynamics, and AI vision systems, it's been a whirlwind of unexpected scientific breakthroughs.
What a journey through the matrix of knowledge.
I'm Maya.
And I'm Arjun. See you tomorrow.